Let's have a look at our next example, example 3. An inspector conducts a test on 400 light globes at a factory and finds that 17 of them are faulty. Determine a 99% confidence interval on the value of P for the population probability of a globe being faulty. So in this case, remember I'll set up my working in the way that I would do it. First of all, P hat is equal to X over N, which is equal to 17 over 400, and that's equal to 17 divided by 400, so 0.0425. Now, I would be identifying n is equal to 400, and I'll be taking a second, particularly in contextual questions, and especially in contextual questions that talk about justifying the reasonableness, to just evaluate NP and NQ. Now, P is quite small on a range of 0 to 1, so Q is about 95%. I don't have to evaluate Q. You can, but I don't really have to. So I get that value, I multiply it by 400. Of course, I should already know the answer because NP is the expected value, and we got 17, so that's 17. And NQ will be equal to 383. That meets my criteria of being above 5. So that's a justify the reasonableness type of process. Anyway, we've got our N and our P hat, and we're talking about a 99% confidence interval. And therefore Z is equal to, not naught, 2 point something, 58? I can't actually quite remember. 2.58, yep, that's it. So remember, you can get that off a calculator. Z is equal to 2.58. Therefore, the error, the margin of error is equal to Z times the square root of P hat times by 1 minus P hat over N. And that's equal to 0.02602. Of course, I keep that in my calculator to maintain accuracy because my confidence interval at the 99% level is P hat minus, so that's 0.0425 minus 0.02602, and that's equal to 0.0165 to 4 decimal places, and then I also add it on, and I get 0.0, so that should be a 0.685, and that is my overall confidence interval for where my p-value lies on a sample of 400, but at 99%. So it's a reasonably large sample, which compresses my confidence interval, but it's also a large confidence interval, 99% being a large one, so that widens it out again. And this is pretty wide, really. The confidence intervals between 1.65% and 6.85% of globes will be faulty in this particular factory. Finally, let's have a quick look at example 4, which is possibly a complex unfamiliar. A biologist has tested a new growth hormone on 600 trees and is confident that between 55.35 and 64.65 of the trees responded well to the treatment. Calculate the level of confidence used, correct to the nearest whole number. Assume normality applies. So this is important, but it's kind of got to be a given because we can't do this unless we assume that. We want to calculate the level of confidence, and the level of confidence is directly related to, so level of to the z-score that's used. Remember, our level of confidence of 99% is a z-score of 2.58. We do that straight transition across. We're going to have to backwards design this using our calculator, but that's okay. We can determine that level of confidence easily at the end. What we need to do is determine the z-score that calculated this. So what I can do is I can evaluate, first of all, n is equal to 600. I don't know p hat, and I don't know x, and I don't know z. So all I've got is n, but I've also got a confidence interval. So our confidence interval for, at some level, A, is equal to 55.35% At some point I'll have to convert to a decimal, to 64.65%. Now, I can work out p hat. Take a second to think about this. P hat will be the median of these two, because I'll know that in equation 1, I get p hat minus e, our margin of error, is equal to, and I'll do this now, I'll convert to decimals now, 0.5535, and then p hat plus e will be equal to 0.6465, and that's the second equation. If I add these equations together, I get 2 p hat is equal to 1.2, and p hat, surprise, surprise, it's a nice number, is equal to 0.6, or 60%. P hat will be the median between these two values. And we've seen that because it will be, we're subtracting e and we're adding e. So there's our p hat. We've got one thing. Now, of course, we don't need to know x, but if we did want x, remember p hat is equal to x over n. And so therefore x is equal to n times p hat, which is 60% of n, which is 360. So 360 trees responded well to this treatment. If we needed x, that's what we could get. What we need is the z-score. So I'll just move this down. We know, therefore, that 0.6 minus e is equal to 0.5535, which means that e, if I just subtract 0.6, multiply by -1, whatever, is equal to 0.0465. There's my e value. That means that z times the square root of p hat 1 minus p hat over n is equal to 0.0465. And so z is equal to 0.0465 divided by, and I'm going to do my substitutions now as well, p hat 0.6 times 0.4 over 600, our n value. And so I'll just quickly do that calculation. And I get a z-score of 2.325. So I want to know what percentage accuracy, level of accuracy am I getting for that z-score. Now, just out of interest, 99% confidence interval, 2.58 z-score. 95% confidence interval, 1.96. So, I'm thinking 98, maybe 97. But let's do this. Let's backwards design this. I know my z-score. And so a normal distribution would look like this. And there's the center, mu. My z-score is here, 2.325. But I want to know how much data lies between it. That's my level of confidence. So between that and negative 2.325, what's this data? So if I work out the tail, that's probably my easiest way to go. Say I work out that tail. I double the tail and subtract that from 100. That'll give me a percentage confidence interval. So I'm going to do that very quickly. So I'm going to go into statistics because I know the syntax for statistics. Distribution, a normal distribution, a normal CD, and I can do a few different ways, but let's say I know the lower and upper. I could actually just do it straight with the lower and upper for the normal CD. So what percentage of the data lies between negative 2.325 and positive 2.325, where I've got sigma is, so this is back to our standard one, is 1, because they're z-scores, and mu is 0, and that gives me 0.9799. So we get our probability that z is between negative 2.325 and 2.325 is equal to 0.9799, which is of course a 98% confidence interval. A 98% confidence interval is taken for this situation. So that's the end of the confidence intervals and the end of this topic. Hopefully that makes sense. Our work is primarily around this formula, and then using z-scores and probabilities, so between 0 and 1, and converting that back out to context. And of course, if you've got any questions, make sure that you ask your teacher. All the best.